We now find expression for gravitational potential at a point due to a hollow shell. Let this circle represents a hollow shell. Now we have to find out potential at this point P due to this hollow shell. Now let the center of this hollow shell be at a distance a from the point P. So m is mass of the hollow shell, r is radius of this hollow shell, and a is the distance of the point from the center of the shell. So we have density of the cell is m by 4 pi r square. This is mass per unit area of the shell. Mass per unit area. Now let us cut this cell by elementary strips by drawing perpendicular planes. Say this is the point EF and GH. Say this is the radius, this angle is d theta, this angle is theta. Now the cut section appears like this. Here is the center of the cell. If this is r, this is d theta, then the arc will be r d theta. This is the radius of this cell. This distance is a. Suppose this distance, that is distance of the circumference of this cut section from the point P is a, say r. Now we have this is O. Now we have to find out the potential at P due to this elementary ring. So first of all, what is the area of this elementary ring? The area of this elementary ring will be, this is, this angle is theta, so this radius is r sin theta. So 2 pi r radius into the thickness, 2 pi radius is r sin theta into the thickness is r d theta. This is the area. Therefore mass of this elementary strip is, we have per unit area mass is m by 4 pi r square. So therefore for this area mass will be m by 4 pi r square. So this pi cancel out, this r square cancel out, 2 becomes this. So this is m by 2 sin theta d theta. This is what the mass of this elementary strip. Okay, now this distance of this elementary strip from every point on the circumference of this ring is r only. Therefore the potential at P due to this elementary ring will be equal to minus g mass of the cell, that is m by 2 sin theta d theta, minus g m by r, distance is r, that is minus g m by 2 r sin theta d theta. Now this is potential at P, let it be dV, due to this elementary ring. Now if we take this type of ring here, there will be two variables, one is theta and second is the distance. Now this equation contains two variables, that is theta and r. So we can integrate this equation from 0 to from this point to this point to get the total gravitational potential for all the elementary strips. But first of all we have to convert this equation in terms of one variable. Okay, now in this equation, this is the triangle, this is O, this is P, this distance is A, this is radius, this is the R, this is the point, say E. Now in this angle is theta. Now using properties of triangle, we can write r square equal to, r square is radius square plus a square minus 2ra cos theta. Okay, now let us differentiate it. 2r dr equal to, this is constant 0, differentiation of a is also 0, 2ra, differentiation of cos theta is minus sin theta d theta. So we have sin theta d theta is this r dr by ra equal to sin theta d theta. This is equation number 2. Now if we replace the value of sin theta d theta here, so we get dv equal to minus gm by 2r, and sin theta d theta will be r dr by r dr by ra. So this r cancel out. Thus we find that the potential is defined as minus gm by 2ra dr. Now this is the shell and the point lies here, this distance is a. So we can imagine that the shell is made up of many such strips. So therefore if we integrate this equation from here to this point, now we will get potential due to the whole shell. So when the point is here, the value of small r will be a minus r, and when the point is here, then the value of r will be a plus r. So let us integrate this equation. So therefore potential is equal to integration of dv, integration of gm by 2ra from a minus r to a plus r. This is dr, that is minus gm by 2ra. Integration of r is this, with lower limit a minus r to a plus r. Therefore potential is equal to minus gm by 2ra a plus r minus a, this minus becomes plus r, that is minus gm by 2ra into 2r, that is minus gm by a. Thus if we keep a point mass here equivalent to the mass of this shell, and we find potential at this point at a distance say because of this point mass, then also the potential become equal to minus gm by a. So thus we conclude that to find the potential at a point due to a hollow shell, the whole mass of the cell can be assumed to be concentrated at its center. Okay, it can be treated as a point mass. So this equation gives the potential at this point P. Now this is case 1, when the point lies external to the shell. Suppose the point is on the surface of this cell. Here we have to find the potential. Then the value of small r is 0, and when at this point the value of small r is 0, at this point the value of the elementary strip from this point will be 2r. So if we integrate the equation 1 from 0 to 2r, we get the total potential gm by 2ra dr. So that is equal to minus gm by 2ra. Integration of dr is r, putting the upper limit 2r, and here the distance of this point from the center of this cell is small a. Small a is nothing but r, that is minus gm by a, that is minus gm by r. So this is equation number 3. So therefore potential on the surface of this cell because of this cell is also minus gm by r, which is a constant. Potential at every point on the surface of the cell is constant. This is very important. See, if the potential is constant, then intensity is potential gradient. So differentiation of potential gradient. Now because this is constant, so differentiation, sorry, intensity is defined as potential gradient, that is rate of change of potential with distance. Now because potential is constant, therefore intensity is 0. So this is very important. Potential at every point on the surface of the cell is constant and intensity is 0. Now case 3, we will find potential at a point inside the cell. So suppose this is the cell and we have to find out potential at this point. Say the point P is here. So this is the distance of this point from the center of the cell. So here the value of r will be that is small r is equal to r minus a. This distance is a, and when the point is here from this to this, so this total distance of this cell will be r plus a. So we can integrate this equation 1 from r minus a to r plus a minus gm by 2ra dr that is equal to minus gm by 2ra. Integration of dr is r. If we put the value of upper limit is r plus a minus r, this minus a becomes plus a because outside there is a negative sign, so r cancel out. This becomes equal to minus gm by 2a 2ra. So this 2a cancel out, that is equal to minus gm by r. So what we see from this equation say 5, that potential on the surface of the cell and potential at a point inside the cell are same. and it is constant. And if we find the intensity, then intensity is differentiation of potential with respect to distance. Because potential is constant, therefore intensity is 0. This is very important, that potential on the surface of the cell is constant everywhere, and potential inside the cell is also constant, which is equal to minus gm by r, and intensity is 0 inside the cell.